Great. Hi everyone. Good evening, good morning, and good afternoon to in whichever part of the world you are. That counts to you. And today we have a session on natural language processing where we will be covering aspects that would give you a perspective on the why, what, and how of NLP. And what's more exciting in this session is it will be taken by Dipanjan Sarkar. Dipanjan is a passionate data scientist and is currently working as a data science lead at Applied Materials. He's a very well-known and a popular name in the data science community, and he's also a Google developer expert in machine learning. With that, I'll let Dipanjan take over the session. Dipanjan, it's all yours now. Thank you. Thank you for joining us.
Sure. Thanks a lot, everyone, for tuning in, and thanks for having me here. So I'll be basically covering some aspects of, you can call this session as NLP 101. So some essentials regarding some concepts, some examples, and some case studies related to NLP. So just a brief about the agenda. We'll be having some basic introduction, then I'll be covering what is natural language, what is NLP, which is basically natural language processing, some motivation around NLP as to why do we need NLP. And then we'll look at what are some popular natural language processing applications out there, cover a standard NLP workflow, which we typically follow to solve any regular NLP problem in general. And I'll also cover some hands-on tutorials, which should be useful because we'll walk through some code and kind of see some NLP applications. And the last part is, assuming we have enough time, I'll cover kind of one or two industry case studies where we have leveraged NLP in the past. So a brief about myself. I'm a data science lead at Applied Materials, and I'm also an author. I've published several books in machine learning, deep learning, NLP, and so on. I'm also working on a new venture with regard to a book, maybe more details later on that. And I'm also a Google developer expert in machine learning. So just a second. Yeah. So this is something which folks interested, you can take a note of this right now. All the code examples which I'll be sharing, and even the deck for the matter, is in the GitHub repository, which is redirected by this link. So feel free to take a note of it. I'll again share it maybe at the end of the session. I'll just pause for a minute here for people who might want to take a note of this. And maybe someone can also type it in the chat for folks on Zoom or YouTube. Okay, so moving on. So what is natural language? Before we get into NLP, we need to understand what is this natural language perspective about. So basically, natural language is kind of a mechanism in which humans kind of communicate with each other, and now basically with machines, because that is where NLP comes into perspective. And it's very different from a constructed or a programming language. As you know, you have fixed functions, fixed methods, fixed constructs when you use any programming language, be it Python, Java, R, and so on. But human language is kind of not so fixed because there are so many combination of words. Each word may have multiple meanings and the way you use it. So that's why, due to the highly unstructured nature of this data, it becomes more challenging to handle it. And typically, there is text and speech with regard to the data, which can be used for NLP, conversational interfaces, and so on. And obviously, it is definitely difficult to parse and comprehend by machines. And that's where NLP comes into picture, because we need to handle text data slightly differently from what we do with traditional machine learning, let's say models handling data from databases and more of relational data. And text data is available in various forms like emails, messages, documents, blogs, so on and so forth. So let's go into what is natural language processing. So to formally define NLP, NLP is basically an intersection between the fields of computer science, linguistics, and artificial intelligence. The main concern of NLP is to understand the interaction between computers and humans, or the natural language as we call it, and basically enable us to be able to train computers in such a way so that we can process, analyze, and model this natural language data. So the whole perspective here is to understand this natural language in such a way that we can perform slightly more complex and sophisticated tasks with regard to understanding language, processing it, and basically applying it in various applications, which we'll see shortly. And there is a lot of material out there with regard to NLP. Then someone calls it text analytics. Some people even call it text mining. So just wanted to clear out some doubts with regard to this. Basically, all of these kind of mean the same thing. It's basically applied linguistics, where we are leveraging statistical techniques to extract different types of concepts, relationships, and patterns from the text data. And now, besides statistical techniques, we also have deep learning models and even deep transfer learning, which has come out in the past several years and have recently gained prominence. The whole idea is to transform this unstructured data into some level of useful information, meaning, relationships with regard to extracting this information from the text data. So what's the motivation behind NLP? Like, why do we really need natural language processing? So this is a very useful, I would say, quote, which comes in from Yahoo Research. So the idea here is that in general, when you go to any enterprise or any company, often you will feel that a lot of information or a lot of data is present in, let's say, Hadoop tables or SQL databases, relational databases for that matter. Now, that data is usually structured, easy to mine, easy to aggregate, easy to process, and maybe show in the form of visuals and do some analysis on it and build dashboards maybe. But I would say one of the important facts here is that it's not just about relational data, but 80% of data in the enterprise is coming in unstructured form, right? That's where the text data or NLP comes into factor, where you need to think about how do you want to tap into this vast information which is present in the form of unstructured data. So that is where this unstructured data can come in the form of typically text data, which could be logs, messages, blogs, articles, documents, so on and so forth. So the whole idea here is there is a lot of unstructured data in any enterprise. And since it's harder to tap into this information, usually people often have the misconception that relational databases is where all the information is at. But nowadays, that is why NLP has gained a lot of prominence, because every company is trying to invest dedicated data science teams to tap into this data and extract the right kind of insights. So again, this is not to dissatisfy or flare up people who really love, let's say, image processing or working with images. But realistically, if you look at all types of companies, all types of domains, and all types of industries out there, there will be kind of a niche domain where you would have to do these kind of activities, where you do a lot of, let's say, vision-based recognition or detecting traffic out there, finding the total number of vehicles, and so on. So granted, computer vision is a huge field, and there's a lot of use in a lot of domains, including things like healthcare. But something you need to remember is, if you consider a more generalist approach as to, okay, I'm kind of trying to build a career in data science. Now, I'm not yet sure which domain I want to focus on. That is where NLP is going to be useful for you, because no matter which domain you go into, they will have some form of text data. There will be many companies which maybe don't work that much on image data, but they will definitely have some level of text data. And that is where you need to kind of have that motivation to learn NLP, so that you can process this data and extract the right kind of insights. And also these days, with a lot of frameworks, which some of you might already be knowing, like scikit-learn and then Spacey, NLTK, now Hugging Face has released Transformers a while back. So with all these nice frameworks and APIs available, it's realistic and affordable to build these NLP models. You don't have to shell out a lot of money. A lot of these methods are all open source models which are available out there, and you can even deploy them in the right way using the right kind of APIs, TensorFlow serving, using PyTorch deployment framework, so on and so forth. So let's talk about what are these NLP applications out there. So in short, there are a vast, I would say, number of applications of natural language processing. Some of the popular ones include things like information retrieval. So basically Google search. So basically it's powered by natural language processing. You type in a query, it will then try to find some kind of a vector representation of that query, and it will find out which are the top similar articles out there or top similar web pages out there based on your query. So that is where information retrieval comes into search. Then we have sentiment analysis, where we are trying to find out what is the sentiment exhibited by customers, by people who are maybe rating reviews, writing reviews, and so on and so forth. We have information extraction, where we are trying to extract key entities, relationship amongst the entities from documents. And of course, I'm sure everyone is aware about machine translation, where we type in or speak in one language and the data gets translated into another language. And we also have question answering applications, where nowadays it's being used in the form of FAQ bots or even chat bots for that matter, where you have some kind of context, some kind of knowledge base. And if you ask questions in natural language, it is able to answer your questions just like, let's say, humans would be answering you. So that's where question answering comes into focus. So overall, if you want to consider applications of NLP, there is a wide variety of applications, and there is also a lot of overlap amongst them, because the features which are used across these applications will be kind of similar, because the features you extract from text data, some level of numeric representation, which we'll go into shortly, those will be reused across any type of application. So if you use, let's say, an application pertaining to document classification, where I need to classify different text documents, like, let's say, news articles into politics, space, research, business, so on and so forth. Even if you didn't have the labels, you could still use the vector representations of these documents and do document clustering. So that's where a lot of the feature representations related to text data can be reused based on the applications. So in short, NLP is basically a combination of processing text data, representing text data in the right way, and then applying some kind of a downstream machine learning or deep learning application. So this is to clear a misconception where sometimes people might think that you don't like NLP is a separate thing from machine learning, and that you need to, if you want to learn NLP, machine learning is something which you need to learn separately. That is not the case, because machine learning is a large part of NLP. And to do NLP, you definitely need to know machine learning. And nowadays, you even need to know deep learning to an extent. So I've summarized the most common NLP use cases in this slide, which you can see. So basically, we have text classification. That is where we already have pre-labeled data related to each text document. And the idea is to classify these text documents in the future, given some new document is coming in. So this is the whole premise of supervised machine learning, right? Classification. So some examples could be support ticket classification. This is a case study we will see later. And I already talked to you about news article classification. So this is where, if I have different types of news articles and I know the labels beforehand in my historical training data, then I can potentially use this in the future, so that if I build a model on top of this, it can recognize new news articles and kind of tell me that, okay, this news article should be categorized under politics or under business and so on. And then we have things like text clustering and similarity, where it can be used in recommender systems. We will actually see a hands-on tutorial about this soon, where we will try to find out similar movies based on the movie description. So that is where document similarity plays a huge role with regard to finding out duplicate documents, recommending similar documents, fuzzy matching, so on and so forth. And a part of these similarity aspects are even used in information retrieval, where search engines like Google are potentially using some kind of information retrieval and document ranking to rank similar documents based on the text query which you are entering. Then we also have other type of examples, where we have document parsing, optical character recognition, where we are extracting, let's say, text from digital documents, doing some kind of entity recognition on that text, right? Where we are applying something called as named entity recognition to extract out the key entities from the text data. And some examples could be entities from health records, legal documents, invoices, so on and so forth. Then we have text summarization, where we have things like topic models, which can be used to extract key topics or trends from a huge corpus of documents. So basically, one document is like, can be a page, can be a blog article, can be even one sentence, and a collection of documents is known as a corpus. So topic models help us in getting the key trends or topics from a corpus, and we can even summarize entire documents to kind of provide a crisp, you can say, summary of the whole document. So this can be like, if I have an entire news article, the news headline could be the summary for that article. So we nowadays have natural language processing models and techniques which can enable us to summarize text documents. And then we have machine translation, which I already talked about, where we are translating from one language to another language. We can translate from speech to text, text to speech, so on and so forth. And then we also have conversational interfaces where question answering systems have become very popular recently with the whole aspect of sequence to sequence models, transformer models, and so on. So the whole idea is, if I have some level of a knowledge base or some level of a context, if I type in questions in natural language, the bot should be able to answer back to me in a just like a human would answer. So that is where we have chatbots, personal assistants, and so on. And the last one here is sentiment analysis, where we can analyze what people are writing about my product, my service, or how people are rating, let's say, the company facilities and their company experience. So we have things like Net Promoter Index analysis, survey result analysis, so on and so forth. So again, this list is not an exhaustive list of NLP use cases, but the whole perspective here is that these are the main use cases potentially in any domain, or let's say any kind of a enterprise which you go into, because these are very common use cases which you need to usually solve using natural language processing. Coming to how do we solve these use cases? So what is the standard natural language processing workflow which we follow here? So this is where this is a workflow which I had built a while back. Again, this is not like something which I've invented, but something which is adapted from a regular machine learning workflow. So this is where we have text documents which are first coming into, let's say, our enterprise or to our systems or servers as inputs. So one of the first steps is we need to pre-process these text documents. So this is where we would need to do some level of cleaning of the text data, because there would be a fair bit of noise in the text data, right? So text pre-processing is all about cleaning my noisy text data. Then we would need to do some level of parsing or exploratory data analysis. Again, this is an optional step. This is where we may want to explore how the documents are structured, parse through to extract the key entities from it, so on and so forth. The next one is probably one of the most important steps in the workflow, where we are trying to represent the text and build some feature vectors out of the text data. The reason for this is text data is in natural language, and any kind of a machine learning or deep learning model at heart is an optimization model, let's say, or an approximation model, which is based on principles of mathematics. So it can only work on vectors or matrices or tensors, so numeric data in short. That's why you can't just dump the text data directly into a downstream machine learning or a deep learning model. You have to use some level of representation to transform the text data into a numeric representation, which can then be fed into a downstream machine learning model. So this block is all about representing text data in a numeric format. And once that is done, we basically go into the flow of modeling or mining for patterns. And this is where, if it's a supervised machine learning task, we can use some classification or regression models. Or if it's an unsupervised learning task, we can use something like similarity or clustering, so on and so forth. And obviously, we will be not just building one model, but multiple models here. And once we build all these machine learning or deep learning models, we would want to see which is the best model, or which model is performing the best, just like a standard machine learning workflow. And that is where model evaluation comes into perspective. And this is where we would iterate with or reiterate with different feature sets, build different types of models, or maybe tune the models, and then kind of see which is giving us the best performance metrics based on what really matters to the domain or to the business, in terms of, let's say, decreasing the number of false positives or focusing more on the true positives, aspects like that. And once we finalize a model, we basically go into what is known as the push to production, where we take in our model, we take in our data transformation pipeline, ETL pipelines, extract, transform, load, and kind of build a whole system around this and deploy this in production. And of course, things don't end here. There are many more aspects to this, like retraining models over time, checking to see if new features are coming into our data, things like that. But overall, these are the key steps which are followed as a part of any natural language processing application workflow. Something to remember is, again, this is not going to be covered as a part of today's scope, since this is more of a fundamental session. But folks who are interested more into, let's say, deep learning for natural language processing, often you would not need to do a whole lot of text pre-processing and you wouldn't need to do a whole lot of extensive data cleaning before you go into, let's say, the feature representation or the modeling phase. You can directly go into the feature representation and modeling phase when working with, let's say, more complex models like transformers, RNNs, LSTMs, and so on. Just something to keep in mind. So let's talk about text wrangling or pre-processing, which is typically one of the first steps once we get our text data. So there are a number of steps here which you can follow. Again, it's not like you have to follow all of them. You can typically restrict it based on the problem you're trying to solve. But some of the main steps here include removing HTML tags, removing extra white spaces, new lines, special characters, symbols. If we are dealing with accented characters, maybe we want to convert them to an ASCII format, which is a standard format. Stemming or lemmatization, just something to remember here is that we don't want to do both of them. Sometimes people make a mistake where you first do stemming and then do lemmatization. Just keep in mind we should either go with one of them, depending on, again, you may need to try both, but if you want to keep the semantics of the words, you need to go with lemmatization. Removing stop words, again, a common thing where we remove words which are not contributing much overall in terms of meanings. And then we need to do tokenization if it's really needed. Spelling check, grammar checks, again, optional, depending on the type of application you're trying to build. So before we go into text representation, maybe I'll just show you how to, some basics of data wrangling or text wrangling. So again, for everyone, this is the link, bit.ly NLP101_DS. So if you go to this URL, it should redirect you to this GitHub repository. So feel free to bookmark it or something so that you can check out the code and the presentation. Now, moving into my first notebook here. Again, try to understand the basic principles behind it. You don't need to understand each and every line of code. It's all available. The idea is to see what is my input, what is my output, what is the process I'm following. So just installing a bunch of dependencies here. So one of the key things could be case conversion. Usually it's recommended to transform all the text to lowercase. And that is where we have, let's say if we have a sentence here with the variable called text, we can just do a dot lower and it will transform it to lowercase. Similarly, we have uppercase, title case, where it capitalizes every first letter in each word. Now let's look at tokenization. So assume we have a big document here, by the way. As you can see, it's a pretty big document with multiple sentences. So one thing could be where I want to analyze or look at each sentence separately. So you can use the sentence tokenizer from NLTK here to tokenize and get each of the sentences separately. So if you run sentence tokenizer on a document, you will get a list, a Python list with multiple sentences. If you want to tokenize based on each and every word, you can use the word tokenize function and you will get a list of all the words across all the sentences, basically. Similarly, for folks interested in using Spacey, you can create an NLP construct on your text data. And if you type in object.text for every object in your sentences, if you see here, I'm using the SENTS attribute here. So if I use the sense attribute here, I will get the list of sentences pertaining to my document. And if I want to get all the words, just like word tokenize, you can just remove the .sense attribute and you will end up getting all the words as tokens from your document. Next important thing is removing HTML tags and noise. So assuming, let's say we are scraping data from the web, this is where it comes in handy, because often when we are extracting data from web pages, what happens is, as you can see, unnecessary HTML tags come into picture, where like paragraph tags, emphasis, bold, line breaks, so on and so forth. So the idea is, how can I extract the useful text information from this? So that is where we can use something called Beautiful Soup, where you can mention that you want to extract only the text content of it, and you want to remove anything related to script tags or iframe tags. And once you typically run this function, as you can see from this huge block of HTML tags and text, you get only the relevant text content. So this is where we can strip out the HTML tags. And this is a standard thing where I'm removing extra new lines and just keeping one new line per line. Next thing is removing accented characters. So as you can see here, I'll just zoom it slightly maybe in case someone is not able to see, but basically you may have accented characters if you're dealing with some form of text, let's say, and some text documents may contain these accented letters. So the idea is if you want to do feature representation letter, TXT as natural English language and TXT with an accented E may be treated differently. So if you don't want that to happen, if you want to maintain some level of standardization, you can do an ASCII encoding here. And what happens here is after you normalize this using the canonical formats, what will happen is you will get it in natural English language and the accents are removed basically from these characters. The other part is removing special characters, numbers and symbols. So one of the simplest ways would be to just use a regular expression. I'm sure some of you must be aware about this, but this is where we uh, build a pattern and kind of say that anything which or any character which is between small a to small z or capital A to capital Z or between 0 to 9, the digits, or having a space, keep it as it is, but otherwise remove everything else. And if we want to remove the digits also, that is where we say that only keep everything which is basically letters and alphabets, and of course the spaces. So as you can see, even if I have emojis or special characters and so on, I can call in this function and remove everything. Of course, if I want to keep the numbers, in some cases numbers are important, you can then run the appropriate regular expression, which is basically this one, so that all the numbers are also kept in. Next thing is contractions. So contractions are basically aspects where we have words with some of the syllables removed, and you have typically a contracted format or a shortened format of the word. Like as you can see, I'd is actually I would, wouldn't is actually would not, and so on. So the idea is I need to standardize this so that this is expanded into the two words, which is actually representative of this shortened format. So that is where basically there is a contractions package, which in short is just a dictionary mapping where it maps every contraction to its expanded format. So it is recommended that you fix your text by expanding all the contractions. As you can see, wouldn't gets expanded to would not based on a simple string matching in general or a token matching. And in this way, you standardize your text in the form of removal of the contractions and expanding them. Next part is stemming, where stemming is concerned only about the syntax. It doesn't care about the semantics or the meaning, which means any kind of a stemmer. In this case, we have used the popular Porter stemmer. There are many other stemmers also, like Snowball stemmer, Lancaster stemmer, and so on. Feel free to check it out. But the basic premise of stemming is there are different forms of words due to inflections, like jumping, jumps, jumped, are all inflections of the same root stem, which is jump. So that is where we want to get back to the root stem, so that even if there are different forms of the same word, we ultimately standardize it to just one word. But this is where it is kind of based on if else rules. Like sometimes it will check whether the word is ending in ed or the word is ending in e and so on, and it will just chop off those or make some transformations. Like as you can see in this case, lying gets transformed to lie, which is the base root stem, and strange gets chopped off to strang. So the whole aspect with regard to stemming is we get the root stem, but that may not be a dictionary or a lexicographically correct word. It may not have meaning. So this is something to be careful about if you're trying to build some models where you want to do some interpretable machine learning or things like that, where you want to explain which were the key features, let's say, which led to the model to predict X or Y, so on and so forth. And that is where lemmatization comes into picture, which kind of takes care of the semantics also. So this is where it looks at a dictionary. Ultimately, we need to look at a dictionary to make sure that the word which we're shortening to, which is known as the base form or the lemma in case of lemmatization. So a lemma is basically a shortened version of any inflected word, which is available in the dictionary, which means basically which has a meaning. So as you can see here, it uses the WordNet dictionary. NLTK uses the WordNet dictionary to lemmatize or shorten every word, every inflected version or a form of a word into its lemma or the base form. And the parts of speech tag, again, parts of speech, by that I mean things like nouns, verbs, conjunctions, prepositions, adjectives, and so on. So the parts of speech is essential for lemmatization to make a correct shortened form. So as you can see here, cars and boxes are actually nouns. So if we pass in the right parts of speech, it becomes car and box, the shortened version of these inflected forms. Similarly, running, ate are verbs, and as you can see correctly, it has made it into run and eat, standardizing the words, basically standardizing different versions of the word.
Dipanjan, hi, Anisha. Hello.
Yes.
Hi. Sorry to interrupt you. Actually, I was confused between lemmatization and stemming. Can you give some like examples in which case we use stemming and in which case we use
Yeah,
lemmatization?
I'll give the example maybe shortly, but in general, what you need to remember is that stemming, we don't care about the base form, whether it has a meaning or not. It's all about syntax. So, in short, stemming is based on a bunch of if else rules, which go through the text based on the kind of inflection which is there, be it ending in ed, ending in s, things like that. And sometimes it will chop off, sometimes it will do a transformation. But lemmatization will always ensure, as long as you pass in the right parts of speech, you will get back the base form, which carries a meaning. As you can see here, strange, strang doesn't really have a meaning. But in this case, as long as you are using the right parts of speech, you will end up with a base form, which is having a semantic meaning at the end of the day. And one
Correct.
thing to
Like,
also, yeah, I'll cover that. Don't worry about that. I'll cover it. So now another thing to remember.
Hey, Dipankar, one question as well.
Yeah.
So we saw that for the stemming for strange, it became as strang. What would be the result of a lemmatization for a, let's say, stranger in this case? Can we see the
So
result?
it's not running here, but you can run it with the
Oh,
right verb. And yeah, because we have only 1 hour, right? And there is so much to cover.
right,
But
right.
feel free to run this in Colab. If you run it with the verb tag, it will become strange, basically. So that's the
Yeah.
whole aspect where you will end up, as you can see, fancier becomes fancy. So similarly, stranger would become strange because that is where the base form comes into picture, which is having a semantic meaning. So that is something to remember. And one more thing to remember here is, I will just cover this quickly, is if you have, let's say, a full sentence, you would need to transform this first into the parts of speech tags, where DT is like a determinant, JJ is like a adjective, these are nouns and so on. And then you would need to transform this into the WordNet pause tags, because lemmatization works on the WordNet nomenclature. So as you can see here, every parts of speech tag, you need to shorten it to the right mapping. And once you have this mapping, now let's see if we do it without this mapping, right? So if we just do wordnet.lemmatize word and tag, and here again, as you can see here, just a second. Yeah, if I just do wordnet.lemmatize token, by default, the tag is taken as a noun. So as you can see here, sleeping, jumping, these are not getting lemmatized. And the reason is, if you don't pass the right parts of speech tag, it will think that, okay, this is a noun, and then it will not lemmatize it correctly. But if you extract out the parts of speech related to each and every word, right? This is the parts of speech tag. And now you lemmatize it with the tag. You can see that sleeping, jumping, these are all getting lemmatized. So just something to remember. And this is a function you can use in the future also, is that whenever you're lemmatizing, the parts of speech tags are essential. Otherwise, the lemmatization won't be effective. And to answer the question again as to where we use lemmatization stemming, in general, if you have a lot of text data and you don't care about the meanings pertaining to the words, but more about standardization, like text classification. Even if you standardize it with stemming, that is fine, because we don't care about explaining the meanings, maybe of which are the most important features. But if you want to explain our classification models, let's say with the most important features, that is where, if you want to explain that, okay, these were the features and you want them to be meaningful, then you need to go for lemmatization. But remember, lemmatization is a more expensive operation because it needs to look up into the dictionary. And of course, it needs the parts of speech tags. Now, moving into the stop word removal, basically the idea is you have a standard set of stop words, as you can see, which don't carry much meaning, like pronouns, uh, connecting words, conjunctions, things like that. And the idea is to remove these as necessary by just doing a lookup pertaining to each and every word and removing them. That is all stop word removal is. Now you can add new stop words, you can remove new stop words, because at the end of the day, it is doing is it is going through each and every token in my list of tokens in a sentence and matching it. So that is where if you want to remove English stop word, or if you want to add in a new stop word, even you can do that. So let's move into the meat of the presentation, because there is a fair bit to cover. So the next part is representation of text data. So this is where we need to transform the text data into some kind of a numeric format. So the most common methods include bag of words, where every document is represented by a vector, where each column in the vector is typically one word. And the values of the vectors are basically the number of times every word is occurring in that document. We'll see a short example of this soon. The bag of n-grams is similar to the bag of words, where we have a vector of numbers, and the only thing is, instead of just single words, we can also have a collection of words which are occurring in sequence. Like if we have a collection of every 2 words occurring in sequence, that is known as a 2-gram or a bigram model. So in bag of n-grams, we just don't have only words, but also a collection of n-grams in the vector representation. TF-IDF is basically a normalized version of the bag of words or the term frequency model, where instead of showing the number of times every word is occurring in each and every document, we normalize it by scaling with the inverse document frequency, which is basically the number of times a word is occurring across all the documents. So you can imagine that if a word is occurring in almost all the documents, it essentially becomes like a stop word or not a very useful word. So if you divide it by the inverse document frequency, or actually you multiply the TF by the inverse document frequency, since the IDF is so high, it will end up reducing the weight of those words which are occurring in each and every document. So that is where TF-IDF is used to downplay the effect of frequently occurring words. And the last one is more of a derived feature from bag of words or any other similar features like embeddings in the future, where you kind of assign score to each and every document with regard to how similar it is to other documents. So based on the base bag of words or the TF-IDF vectors, you can assign scores to every document as to how similar it is to each other document, also known as the pairwise similarity. Let's quickly look at an example of this. So again, this is just a sample corpus. Considering the time at hand, I won't walk through each and every line of code, but you feel free to refer to this. This is just building a standard data frame where we have these documents. Now, the whole idea is, how do I represent each of these documents into a numeric format? So for that, I do some basic text pre-processing. As you can see, all the text for the documents are lowercase, the stop words are removed, and so on. And then I apply the bag of words model, which is called count vectorizer in terms of the scikit-learn APIs which are available. So if I apply the count vectorizer on every document, this is how it looks like. So you can see that every word is a part of my vector. So like this is the vector, this first row is the vector representation of my first document. And as you can see, the first document was all about the sky is blue and beautiful. So this got pre-processed into sky, blue, beautiful. So these are the 3 words which are occurring once. So in my vector representation, as you can see, beautiful, blue, and sky are occurring once. All the others are 0. So basically, it will be like a sparse matrix where only the words which are occurring in that document will be marked as a non-zero value, depending on the number of times that word is occurring, and all the other words will become 0. So this essentially becomes like a numeric matrix, which you can then feed into a downstream machine learning application. For the bag of n-grams model, what happens is we can, instead of looking at just words, we can look at sequence of words. So beautiful sky occurs in sequence in the second document. That is why it is marked as 1. So the number of times every n-gram is occurring in the document, we basically put that count in place of that n-gram, and we have similar vectors again. Something to remember is, as you increase the number of n-grams, the dimensionality of your vectors also starts increasing. So just something to keep in mind, because you don't want to get affected by the curse of dimensionality, which can overfit your models. And like I said, for TF-IDF, what happens is we basically multiply it by this inverse document frequency. And this inverse document frequency is the log transform of the total number of documents in the corpus divided by the document frequency of the word. So obviously, if a word is occurring in each and every document, the IDF ends up really being a small number. So if you multiply it by the term frequency, as you can see that we start getting floating point numbers, which are essentially normalized versions of the counts. So TF-IDF is sometimes useful when you want to downplay the effects of words which are occurring very frequently in the corpus. And document similarity is where we can use these vectors which we get and try to say that, okay, how similar is document 0 to document 1 based on these vectors. And once you do that, you typically get like a pairwise similarity matrix where you can kind of say that for document 0, how similar are all the other documents. In our case, we have around 8 documents. So you can see here that for document 0 here, obviously document 0 will be the most similar to it because it is exactly the same. But what we are concerned about is all the others. So from this, we can easily get insights that document 0, 1, and document 6 are very similar to each other. So if you see here, document 0, document 1, and document 6 are all related to weather. So here I have used a basic clustering algorithm called k-means. And if you pass this similarity matrix to k-means, what it helps you do is it helps you group the documents. So you can see that even if I didn't have the category, I would know that, okay, which are the similar documents which are occurring close to each other. So this is where you can start using these features in downstream machine learning applications like clustering, classification, and so on. And we'll see an example of this soon in the hands-on tutorial. Going into the next one, this is something you can dive into more detail when you get time, but this is where we leverage word embedding models, where we use some kind of neural network backend models to generate these text representations, where instead of just doing a count based on every word, we kind of look at each word and the surrounding words to generate dense vector representations of each and every word. And there are various variants to this. The most popular ones include Word2Vec, which was invented by Google a while back. And then we have GLOVE, which is called Global Vectors from Stanford, where it uses a similar but yet different mechanism in the form of matrix factorization. So it uses a matrix factorization technique, in short, to obtain dense word representations. And FastText basically uses a bag of character n-grams to represent these vectors in the form of dense vectors, every word. So in Word2Vec, every word is represented as a single entity, but FastText takes that one step further by considering a word as a combination of subwords. So you can see that the vector for where would be a combination of all of these character n-grams averaged together. So each of these character n-grams will have their own vector representation, and then you can combine them to get the representation of where. And this really helps us when we have out of vocabulary words where you can combine vector representation for that word using character n-grams. Not covering this in too much detail due to the complexity of this, and also keeping in line with the time which I have left. But if you're interested, I would recommend you to go through this book, go through this notebook where again, I'm using the same documents here, but you will basically be able to see that I use the GenSim package here to generate a Word2Vec model. And essentially what happens here is, since I can generate a vector representation of each word, you can see that all the adjectives and animals, and here all the things related to breakfast and all the things related to sky, beautiful blue, they are all grouped together. And the reason is these are the vectors, which is the output of the Word2Vec model. So in my case, I had told that the vector representation for every word should be of a size 15, a vector of size 15. So every word here is represented by a vector of numbers of size 15. And the whole concept of Word2Vec is similar words like, let's say, sky, blue, and beautiful will have vectors which are very similar to each other. And that is where you can use document similarity again, like we saw before, and we can compute the similarity of each word to other words. And you can see like sky, blue, and beautiful are having a really high similarity versus other things. And the whole reason is because these numeric representations have been trained using a neural network in the backend. Something to check out in the future once you read up more on feature representations using embedding models. Let's talk about the most important aspect of once I convert text data into numeric representations, how do I use it? So that is where we can build classification models, we can build recommender systems, we can do clustering, topic modeling, sentiment analysis, semantic analysis, and so on. And some of the real world challenges in the industry is to really understand what is the problem, because no one from an enterprise will come to you saying that you have to do sentiment analysis on this data set. Usually they will come with a very vague problem statement. And that is where you need to understand how to frame the task properly, whether it is classification, NER, information extraction, and so on. So understanding how to frame the problem is one of the most important challenges first, and then you go into the model training, debugging, so on and so forth. And some of the challenges here is with real world data, uh, you will see that you may not get 90% accuracy. So that is where you need to think about when should you stop training or tuning your models, and when it might be ready for deployment. So that is where the whole aspect is, you don't know unless you really try it out. So the whole thing here is you need to reiterate across different versions of features, models, and so on to see what is the best model you get, and even deploy and see how it works out. Let's look at the hands-on examples. This will give you a lot more perspective. So we will look at two use cases here. Hopefully we have enough time to cover both of them. One is a movie recommender system where we have movie names and the description of the movie. And the idea is based on a new input movie, can I use the description to recommend similar movies? And the other one is a classification problem where I try to predict whether a product is a good product or not, given the review text. So the workflow for the movie recommender system is to get the movie data set, clean the movie descriptions, build the TF-IDF features for each and every description. Like we discussed, we need to convert the description into a vector format, do the document similarity using cosine similarity, which we have used here. We discussed about this pairwise similarity, how similar every movie description is to the other movie descriptions, and then recommend similar movies based on a input movie description. So we'll go into this, and you can read up about content-based recommenders and these aspects in more detail. That's why these notebooks are there. Let me go into the meat of the problem. So we load up the data set here, which is pandas data frame. Once we load it up, the key things of our interest are the title, the tagline, and the overview. So we combine the tagline and the overview to generate the description, as you can see here. So the description column of the movies is of our interest, where we combine the tagline of the movie and the overview. So the main thing here is, given a movie title and a description, can I find out similar movies based on their descriptions? So the first step here is to pre-process the documents. So this is where I do some standard regular expressions, as we discussed before, to keep the numbers and the text, do a lower casing, remove extra spaces, so on and so forth. And once we pre-process the text data, we have around 4,800 movies. The next thing is to do the TF-IDF feature extraction of these movie descriptions. So what we do here is we tell it that we want the words as well as the bigrams as a part of our feature vectors. And we set the min df to 2. What that means is remove all the words which are occurring only once in all the movie reviews. So basically we're removing words which are occurring only once, which means they are not very useful. And in this way, we can reduce the dimensionality of the vectors also. So as you can see, every movie review description ends up being a vector of size, almost a 20,000 odd sized vector. Now the idea is, once we have a numeric vector representation for each and every movie description, we can try to find out how similar every movie is to the other movies. That is where we use this cosine similarity function, and we try to find out how similar every movie is to the other movies using the TF-IDF vector representation. And then you can see that we get a 4,800 cross 4,800 sized matrix. Here I'm only showing you 5 rows, but you get the idea, where I know that how similar every movie is to the other movies. And once I know this, I can use this information where, once I, let's say, take a movie name, let's say called Minions. So what I need to first do is find out where in the matrix Minions is occurring. So as we had seen before, that the movie Minions is occurring pretty much in the first row. You can ignore these indices, by the way. Once you reset the index, basically Minions is occurring in the first row of our data frame or the first row of our matrix. So essentially, this vector points to the similarity of all the other movies related to the movie Minion. So once I take the Minions movie, I find out its position. Once I know where it's occurring in the matrix, I extract out the similarity vector. So what this means is just extract out this row from this whole matrix. So now I know all the similar movies related to Minions. Now, obviously, I need to remove the first one because Minions is 100% similar to itself. All I care about is the other movies. So to get the movie indices or the row numbers, you can use this nice function called argsort. And once you use this argsort function, you use a minus on top of this because I want to sort it in the descending order. By default, it sorts in the ascending order, but I want the most similar movies, which means movies with the highest similarity scores. So once I do that, it tells me that, okay, these are the movies which are most similar. And you can see here that Despicable Me, Despicable Me 2, all of these come out as the most similar movies, which makes sense because they are a part of the same franchise. So what you can do here is you can build a generic function here where you can find the movie ID, you extract out the movie similarities from your matrix, you find the top similar movies, and you print out the top 5 movies. And in this way, you can experiment with some other movies, some other popular movies in this data set, where you can kind of see these examples, and you can see that some of these make sense with regard to them being a part of the same franchise, so on and so forth. So that is where the whole aspect here is using a simple methodology of converting the text description into a TF-IDF vector, taking a similarity matrix computation using a pairwise cosine similarity across each and every movie, and then basically sorting it by the most similar movies based on the highest similarity score, and then showing them. You can easily build a content-based recommendation system. And now what you can do in the future is instead of TF-IDF, you can substitute this with, let's say, account vectorizer. You can try some other feature engineering techniques like using a fast text model, so on and so forth. Going into the next one, this is a standard classification problem where I take in e-commerce review ratings data set. I do some basic text pre-processing, and then I do some iterative machine learning where I build separate feature sets each time using count-based features, sentiment features, and bag of words-based features. And I try to build a classification model to predict whether the model is giving a good performance in saying whether a product is a good product or a bad product. So a lot of concepts will be similar from the last time, wherein this is my e-commerce reviews data set, and I have converted it into a simple binary classification problem, where if the rating is 1, it is a good product, and if the rating is 0, it is a bad product, just like sentiment analysis. So I'm just removing where we don't have any review content, removing those rows. And now, as you can see, it is a highly imbalanced problem where the number of useful products are more and the number of not so useful products or good products are much less. So we do a standard machine learning workflow here where we build a training data set and a test data set, a standard train test split. And then our first feature sets to convert the text data into numeric representations are using counts. So we want to count the number of words which are there in the review. We want to count the number of characters which are there in each review. We want to find out the word density, which is the character count divided by the total number of words. Want to find out the number of punctuations, the total number of words beginning with an uppercase character, so on and so forth. And once we do this, you can see that for each and every review, we have this numeric representation of different properties of these reviews in terms of the number of words, punctuation, so on and so forth. Now the idea is, can I build a classification model using these numeric representations, and can they help me learn good enough patterns to say what is a good review versus a bad review? So this is where we use a logistic regression model as a classification model to build this, and we then kind of try to test the performance. So to test the performance, first we fit it on our training data, and then we predict it on the test data, whatever the model, our trained model has, and then we check our confusion matrix and some key metrics like precision, recall, F1 score. And as you can see here, our model is essentially predicting everything as class 1. So that is why the recall as well as the precision and consequently the F1 score is all 0, which means the model hasn't really learned anything. You give it any review, it will predict it as class 1. So this is not at all useful. So what can we do next? Now, since we are dealing with text reviews, customers will be pretty emotional, or they will express some kind of sentiment in their text. So this is where we use unsupervised lexical sentiment analysis API, which is text blob. I'm sure a lot of you have heard about it. So TextBlob looks at a dictionary and kind of figures out that based on different types of adjectives and different types of words, which is basically having a positive sentiment or a negative sentiment, it can rank or score the words in terms of the polarity, which is whether it's a positive polarity or positive sentiment, or a negative polarity or sentiment, and the subjectivity, which is the level of emotion being exhibited in that document. So what we do is we now append these two new features, the polarity and the subjectivity. So obviously for positively emotional reviews, we'll have a higher polarity score and a lower polarity score for the negative sentiment reviews. So using these two new features, we again rebuild our model, the same logistic regression model. And now what we can see is we are able to classify a fair number of reviews as the bad reviews. So now our recall is around 27%. So 27% of the total number of bad or negatively rated products we are able to predict. And precision is also quite decent, around 69%. And the good reviews performance is obviously better because obviously we have more data for it. But our main focus is, can we improve the performance of the predictions for the bad reviews, because the data is also less for that. So now what we look into next is a standard workflow, which we just discussed, where we keep only the text alphabets. We remove the extra spaces with regard to the document. And as you can see here, we discussed this during the data pre-processing and wrangling. I am stemming every word in each document. And then I'm removing the stop words. So some standard pre-processing steps I'm doing on each and every document. And once I have the clean review, I'm going to use the bag of words feature. So here I'm using a simple 1 gram model where every word becomes a feature. So these are my feature vectors, as you can see, just like we used TF-IDF before. So I'm using the count vectorizer here, and you can see that every word becomes a feature. So our feature space explodes from only 6 to 8 features to now having almost 8,500 features. So what I do next is I append this to my existing features. So what that means is I have the density and the numeric features related to the properties of the reviews. I have the sentiment related features of the reviews. And now I also have the counts related to each and every word across the corpus. So basically bag of words plus sentiment plus density based properties. And considering all these features, I now build a model. So as you can see, once I build the logistic regression model on the training data and I predict on the test data, the combination feature set, my performance really improves. So earlier I was able to predict only around, if I look at this, sorry for the scrolling, but earlier I was able to predict only around 27% of the bad reviews, right? So now if I look at this new model, I am able to predict a lot more. It's actually reversed. So I'm able to predict 70% of the bad reviews. And my precision is also quite decent at 76%. And as you can see, the good reviews performance is also boosted. So my overall precision comes to 88%. F1 score also comes to 88%. So this is where we just saw an example of reiterating and rebuilding the models, right? Starting with simple text count and density based features, and then going into sentiment based features, and finally looking at bag of words based features, and trying to build first a baseline model and improve on top of it by adding more features and seeing whether that's helping us improve the performance of the model. So this is a standard workflow which all of you typically should follow when you are going into building any kind of NLP application, be it supervised or unsupervised. Now, I think I'm almost out of time, but I'll just cover this briefly for the next 5 to 10 minutes. I hope that is okay. So this is basically the whole concept of IT service management, where typically service desks are operated in any kind of an enterprise IT system. And one of the key problems here is incident management. So the goal of incident management is, an incident is when a problem is occurring in your enterprise environment. And that is where someone will call or log a new incident, a ticket will get created. It needs to be categorized, it needs to be prioritized as to how quickly the issue or the problem should be solved. And then we would need to resolve this incident or resolve this problem. And once the right root cause has been identified and the right solution has been identified, the problem is resolved and then it is closed. So as you can see, there are many bottlenecks in this, and the whole idea is, can we leverage natural language processing in some of these bottlenecks to automate it? So what are the AI use cases which can be used or which can be potentially looked at for automating incident management? One thing is the priority or the root cause categorization or prediction. So typically, as you can see, a priority is usually assigned by a subject matter expert manually. So can we automate that? Can we predict what is the root cause of the problem? Can we automatically solve the problem? So these are some of the key, I would say, AI use cases which can be solved using natural language processing. So predicting the incident root cause and the priority. So like I was saying before, in the enterprise environment, they will have their own operations team with support agents who will manually classify, tag, and label the root cause, as well as the priority of each and every ticket. So this leads to a lot of manual effort and wasted efficiency, because their true work is to resolve the problems. So sitting and classifying and labeling, this is something which they have to do so that the tickets can go to the next queue, basically. So the idea is, can this be automated so they can actually spend the time in solving the problems in a more efficient way? So how can we do this? This is where we can look at the historical incident data. So let's say we look at the past 2 years worth of label data, and can we build a classification model which can predict this root cause for future tickets? So this is the opportunity of natural language processing and these machine learning or deep learning models to predict the root cause. So this is where we leverage a historical ticket data where we already have the root causes. Remember, if you don't have the label data, you can't build a supervised learning model. Just like we use logistic regression in the previous data set, remember we had the good and the bad labels. So the idea is, once we have this label data, we can parse and process this ticket description related to each and every incident which we had in the past. We can look at other structured fields also, like the location of the ticket, product which was involved, so on and so forth. We generate text features again. So these text features could be just like a TF-IDF vector or a bag of words count vectorizer based vector, and so on. And once you have the numeric representations, you can apply a logistic regression model, a decision tree model, basically iterate through models to get the best performance. So this is how the sample incidents look like, where you have an incident number, the root cause, the short description. As you can see, there are other fields also like long description and so on. And as you can see, this is the text data which typically would need to be vectorized. So this is a workflow which we followed, and you can see this is very much similar to the initial NLP workflow I talked about. So this is something even all of you can use when you are going into, let's say, building a classification model, text classification model, where you first normalize the text using various steps. You try out different feature engineering methods like bag of words, TF-IDF, or embeddings. If you have a lot of features, you can look at dimension reduction techniques like PCA and so on. And then once you have the numeric vectors, obviously, you can apply supervised learning classification models like linear models like logistic regression, SVM, try out ensemble methods like random forest gradient boosting, maybe even check out deep learning. However, remember, for deep learning, this feature engineering part will be slightly different, where we need to deal with embeddings. And obviously, the final step is the model evaluation and deployment, if you remember, which we talked about, where we find out which model is performing the best in terms of the true positives, the false positives from the confusion matrix, look at the accuracy, the precision, the recall, F1 score. And of course, the most important part in an enterprise scenario, you need to verify that your model results make sense from domain experts. So that can happen in this way, where let's say this is just an example where we have the description, we have the actual root cause. And as you can see, this is our predicted root cause. In many cases, it matches. In some cases, it doesn't match, because obviously the accuracy of a model can't be 100%, right? If it is, then something's going wrong. So this is where you need to validate this with the domain experts and potentially think about building your solution. And the last part of this industry case study is, can we automate the incident resolution itself? Which means if a new ticket is coming in, instead of determining the queue and the other aspects based on past closed tickets where the solution for that ticket was known, can we look at similar tickets and say that, okay, this ticket looks like this should be the solution for it given the past data? So this is where, if you can leverage the past historical data where you already have the ticket descriptions and you also know the knowledge base article which was used to close that ticket, maybe you can predict a new knowledge article for a new ticket coming in. And this can lead to self-heal systems, but it is not that easy. You need to only do that if your model has enough confidence, because otherwise you can imagine if your model is automatically closing a ticket with a wrong knowledge article, that can lead to a lot of bad, I would say, rework later on due to some bad predictions. So that is where the whole concept here is to, the model will predict a potential knowledge article which can be used to close a ticket directly. And that is where we leveraged reusable components from the previous classification models, which I just talked about, right? Where we are looking at predicting the root cause given the ticket description, or predicting whether this ticket should have a high, low, or a medium priority, looking at the ticket description. So in this case, the only thing which changes is the model will predict a potential knowledge article based on the text description. And the other part is based on unsupervised learning, where we have a full knowledge base of tickets and the corresponding knowledge articles. So you can imagine it just like the movie recommendation, right? We have the movie description and we have the movie names. So if I have a new description coming in, can I predict which are the most similar movies? So in my case, if I have a new ticket description coming in, can I predict which are my most similar knowledge articles which can be used to close that ticket? So this is where we had these two scenarios, where scenario one was past knowledge article labels and the incident or the ticket description data goes in, and we build a model. In this case, we used a recurrent neural network based model, but a machine learning model could easily also solve the purpose if it gave a good performance. And the whole idea is, after pre-processing and feature engineering, once we build a supervised model, if a new ticket came into picture, then basically what we would predict is what is the knowledge article which can be used to close the ticket, and the prediction confidence, or the what is my confidence. So what that means is, if my model is having a low confidence score, I don't want it to automatically close that ticket. That is the whole reason of having this prediction confidence. And this elastic block is more about visualizing the results. So all of you, or some of you, might already be knowing about the Elasticsearch framework, where it can be coupled with Kibana and you can visualize these outputs also in the form of graphs and so on. And the last one is the unsupervised scenario, where I am not building any supervised model, but basically I am having a ingestion framework where I am dumping each and every incident description and the corresponding knowledge article which was used to close that ticket. And what I do is I build a search engine on top of this data using Elasticsearch, where if someone types in a query of a problem they are facing, just like, let's say, in Google search, I type in a query in natural language, and what will happen is it will query this data. It will look at the most similar incident descriptions from the last 2 years, let's say, and it will say that these are the most similar problems to your query, and these were the tickets, or sorry, these were the knowledge articles which are used to close the ticket. So in this way, you can have like a preemptive solution where even before a ticket is filed, someone can look up and solve their own problem. So this is like a self-help scenario which we built. So in short, these are the use cases which I covered from the last 5 years, some of the important ones which I've solved. So hopefully this was useful, and feel free to leverage the notebooks which I had shared. And if you want to be in touch with me, these are my kind of social links. Feel free to take them and connect with me if needed. And all the code and everything is available in this repository. I will share this link again. Hopefully this was useful. I'm sorry we had such less time, but otherwise I would have gone in more detail.
Thanks a lot, Dipanjan. I think the session was very insightful, and I got to learn a lot personally, and I can see that, like, a lot of learners are quite motivated and, like, inspired by the session. Before we jump in, and probably, like, I'll try and introduce Gunika, who is trying to moderate on YouTube, and probably, like, we can pick some questions in there.
Sure.
Yeah.
Absolutely.
Gunika, yeah. And also we have on the other side, like, Professor Julian and Raviraj and Gunika were trying to moderate the questions on YouTube, and they were trying to address few of them, but we will pick the unanswered ones. Gunika,
Sure,
you
sure.
can go ahead. Yeah.
Yeah. Okay. So one question that we had on YouTube is any insight into how or why you select certain NLP frameworks like NLTK versus Spacey?
Yeah, this is I would say, a more of an opinionated choice, right? Where based on what you have used, maybe, or what you're comfortable with, you can use it. But see, NLTK is more of like a historical framework which has been there for a long time. So if it was, let's say, 3 years back, I would say you can work with any one of them, NLTK or Spacey. But right now, based on the advancements which Spacey has done recently, including a whole lot of new features related to deep learning, embeddings, and so on, I would say Spacey is the way to go. But NLTK does have some useful interfaces which you can still use in terms of the Stanford core NLP interfaces, which you can easily use with Python instead of having to go the Java route. So it's more of a like your own choice of what you're comfortable working with, and also maybe the performance once you're trying things out. So in from my side, there is no restriction with the tool choice, but I would say Spacey is adding in a lot more features versus NLTK right now.
Mm-hmm. Okay. How do we decide on the n value, like in n grams in this case?
So, in short, anything beyond trigrams is not going to give you useful results. That's what I'm telling you beforehand, and you can validate it. But in general, between 2 grams, bigrams, and trigrams, you can try it and see which gives you a better performance. Sometimes you can do a bigram and then apply a, let's say, SVD on top of it to reduce the dimensionality also and check the performance, overfitting, so on and so forth. But you have to try it in general. But usually I've seen like bigrams is usually more than enough. Trigrams really explodes the feature space, but with dimension reduction, sometimes it can give you a better performance. But don't go beyond trigrams. It's the return on investment, as I may call it, is not that huge.
Yeah, got it. So we also have some questions that were filled in the form during registrations.
Sure.
So one of them is what are the metrics used to test the NLP model, specifically the chatbots and language translation?
Very interesting question. So there are a lot of metrics for sequence to sequence models. So whenever you're dealing with a sequence of words, you can look at things like the perplexity, and you can write these down also and like research more on these. There is the perplexity, there is the coherence maybe, and you have also things like the blue score, which looks at sequences of words, kind of compares it with the gold standard and sees that how many of the words are present, how many of them are occurring in sequence, so on and so forth. So perplexity, blue score, the rouge score, typically common ones often used with regard to these applications based on sequence to sequence models.
Wow, okay. So can you elaborate a bit on how NLP is different from machine learning or deep learning?
Yeah, so like I said in the beginning, it is not completely different. And the only part which is different is since you're dealing with unstructured text data, right? So that is where you need to process it in a different way and do some additional tasks before you can make it usable. So NLP is where you need to handle the text data, you need to process it, you need to transform it in the right kind of a numeric representation, and then basically still your machine learning aspects come into picture, right? So once your text data is in a numeric format, that is where you can use a machine learning model, you can use a deep learning model, and you can solve the problem you really want to solve. So even in the case of, let's say, a sequence to sequence model where you have a sequence of text coming in and a sequence of text going out, like a language translation, you will still need to transform that text data into a numeric representation, and then you use a deep learning model. So I would say all of them are interrelated. The only difference is you need to handle the text data in a different way, and that is what NLP is all about. But NLP is inclusive of parts of machine learning and deep learning.
Yeah.
Great.
Can NLP algorithms understand a mix of different languages in the same data set?
A mix of different languages in the same data set. I haven't really tried it, but looking at the way the transformer models are going, so far I've seen language specific transformers to an extent with regard to fine-tuned models, but I have seen generic models also where you can potentially translate from any language to the other language. Again, not every language in Earth, but at least a fair number of languages. So I think it should be doable, though I haven't tried it, so I can't give you first-hand experience. Yeah.
Great. And we have one question on Zoom. When should we
Um,
use pertained models like birth? Uh, which process needs to be skipped when we use birth models?
Okay, so I will highlight that for you. So if you are using BERT, you can replace all of these and put the huge BERT block in. I think all of you have seen how BERT looks like. So that's where BERT is really fast-pacing NLP development, where you have these pre-trained models which have already been fine-tuned to an extent on a lot of data. So the idea here is you need to do minimal text pre-processing. Don't need to do any feature representations and so on. Of course, you need to do some level of text processing in the way of representation, where you need to create sequences of the text documents in the right tokenized format. But that is all you need. You can plug it into the BERT model and fine tune it based on the task you want to do, like classification, Q&A, so on and so forth. And that is where a lot of the manual effort is being reduced, which needed to be done in traditional statistical or machine learning based NLP pipelines.
Great. And can we use POS tags in our word embedding models?
Maybe it depends. I mean, of course, you can have peers tags also as a vector representation or something, but or you can include that in your text as you are building it. But in general, I mean, at least I haven't used it because it is all about the words, the sequences of the words occurring in front, and the next one, so on and so forth, and building embedding representation. So, I mean, as long as you have it in your text data, it is doable. But I mean, I haven't really used it.
Got it. And there is another question.
Yeah.
Doing text summarization on set of documents provide irrelevant data too. Is there any other way than human filtering to remove sentences which are out of context?
Mm, Honestly, no, because the context is something which is understood by humans. Now, if you can train a transformer model, or if you can train a deep learning or even a machine learning model for that perspective to understand context, then why not? But I think that is very hard to do, because if you see detection of things like sarcasm is something which is still not completely solved. And you may see several papers on it, but a lot of it is again based on models which have been trained on pre-labeled data sets. So if something completely new comes in, how do you detect it? So it becomes harder and harder. Now, let's say if you have models like GPT and so on, which can be used to generate fake news, maybe something like a hybrid architecture, just like generative adversarial network works, right, with a discriminator trying to fool, so on and so forth. So if you have that kind of a pipeline where you can build something where you can automatically filter out or detect which are the bad contextual sentences, maybe it can be built, but it will definitely be a complex system and you will need some ground truth to start with. So in short, it is very difficult. You will definitely need domain experts, but can it be done? Maybe. Yeah.
Right, got it. And this is more of a generic question that I'm picking from the Google Forms. So, what is
Sure.
the most challenging part in implementing NLP in industry for solving business problems?
The most challenging part is, one of the things is, like I was saying, framing the business problem. So framing the business problem can be really challenging, because often you will have a lot of text data and they will say, okay, we want to increase X% sales, or it will be a very ambiguous problem statement given to you. So to figure out whether you need a classification, or whether you need a clustering, or whether you actually need NER as a filtering to your model, all of these parts become very challenging. But one of the most challenging things is, I think, deploying the model. And the reason is because of, in a standard machine learning pipeline, the ETL part of it may be slightly less involving. Again, it depends on the number of features you have, but in this case, you have to handle the text data, pre-process, convert it. You need to transform it. You need to load up your saved model, make the prediction. And I'm sure a lot of people in this call who have used BERT and these other models might know that the memory footprint of these is really high. So to make the inference at, let's say, sub-second latency can be really challenging. So that is where I think model deployment and maintenance becomes a huge challenge, especially with NLP models, because it's not just about the notebooks, let's say, which you saw today. There is a lot more going on once you build the models.
Yeah, cool. And yeah, this is again somewhat related to what Gunika has asked in the past. So, if I have already done ML and machine learning and deep learning, how do you suggest going about NLP? Any good resources? Again, this is a very broad and generic question, but if you can suggest something, that
So
would be great. Yeah.
yeah, I think if you already know machine learning and deep learning, you're well on your way to almost knowing NLP. The only thing is you need to know how to handle the text data. So the main thing is you need to start with, like basically follow this pipeline, right? Like, how do I handle text data? How do I parse data, represent text data? If you know this part, then this part becomes easier. So again, resources, there is a lot of things out there. For reference, you can use some books, maybe like I myself have some books on text analytics with Python. You can check out my GitHub repositories where I have done end-to-end workshops in NLP, and I've covered everything from logistic regression till BERT, distal BERT, GPT, and so on. So if you want, I would say start with a hybrid approach where you not only just learn about the concepts behind these, but also learn how to use them in the form of the notebooks, let's say, which we just saw. So I would say practice the concepts you learn. In that way, you can retain it better, because industry, I mean, most of the things are now applied. Unless, let's say, you're writing research papers, you would need to actually apply these methods and solve problems. So that is where I think following a hybrid approach is best. A lot of books out there, I think, feel free to leverage it with regard to books. Like, I think there are some recent books coming out from O'Reilly on natural language processing. There are books on Manning on NLP in action, so on and so forth. I know even some of them, so they are pretty good. Feel free to leverage these books. I myself have a book on text analytics in Python. I would recommend check out my Medium articles. You will find a lot of things related to the things which we were covering today, right? Like the word-to-vec models. How can you train a model from scratch? These bag of words models, text classification, so on and so forth. So I would say use a combination of hands-on as well as some theoretical concepts related to books. Again, I'm not like a huge like YouTube channel checker, so I won't be the best person to advise, but I'm sure you'll find a lot of articles and other resources out there if you search for them. And if you know MLDL, you pretty much know how to filter out the noise. So you're the expert.
Yeah. Great. Thanks. And then I'm pretty sure, like, you have some quality content out there on Medium. I keep checking
I try to
sometimes.
create. So.
Thanks for that. And one last question, probably before we close the session: how the sarcasm in the input text impact the sentiment analysis?
So you can check with so if you check the BERT models which are out there recently, right? There is a sentiment pipeline for it, and you can use a pipeline framework. It is there in one of my GitHub presentations also for a workshop I did recently. So if you write a sarcastic text there that this movie was so not good or something like that, if you write it in that way, it will still say that the sentiment is positive with a high confidence. So sadly, I think sarcasm detection is something which is very tough. There are many papers out there, but honestly, I think the only way to go about this is creating it as a separate task, along with, let's say, all the other tasks which are there in the multitask learning, which happens in the transformer models, and maybe train a model on that. Because I think if sequence to sequence has been able to solve so many problems like translation, speech to text, and chatbots to an extent, so on and so forth, I think maybe treating it as a separate task, having good enough data for it, may help us learn some representations. But that is where I think the model would need to be first pre-trained before we can use that pre-trained model. So at least from my side, I think that is the only way, unless I think someone invents something which is groundbreaking, just like transformers.
Got it. Thanks, Itan. And I think we have a lot of thanks pouring in on YouTube and also on Zoom. Thanks,
sure,
Itan.
Yeah, sorry, I had to rush. Yeah, sorry, I had to rush a bit to the end, so because there was too much. But yeah, I mean, you can reach out to me anytime to do a deep dive. But I hope it was useful. Yeah.
Thanks a lot. And someone said hi from West Bengal University of Technology, like the session. I mean, like, maybe it belongs to your this thing.
Bachelor's.
So that's something. And also, Dipanjan, on a general note, can you share something on a personal level where you went through the entire learning journey, right, on the data science front? Anything that you would want to share to the beginners and, like, some data science enthusiasts on a personal note?
Sure. Yeah, I would say it's great to see a lot of enthusiasm out there. So I think definitely the right time to dive more into this field. And again, I know there is a lot of hype around this field, and there's a lot of things, even with the COVID situation and so on, with jobs, so on and so forth. But the main thing is, I would say, don't stop your learning, because I mean, of course, I don't publicize it much on LinkedIn, but I still do a lot of courses as and when I get time. That is, I still beta test courses for Coursera. I still do some of my own learning, because what I've realized is, and this has happened to me, let's say in the mid career level or whatever, that where I got a bit too comfortable with my job and I wasn't learning too much. I think happens to a lot of people. Many may resonate with me. So I think don't make that mistake, because this field is so rapidly advancing. And as you can see, with transformers and so many other things happening, just in NLP for that matter, deep learning, so many other things keep happening. So I would say stay up to date on what is happening, but you don't need to stay so much up to date that you like become overwhelmed that I have to know each and every model which is coming out, right? Know the fundamentals with what is how to handle different types of data, how to do feature engineering, how to do feature selection, how to build machine learning models, understand the concepts behind these models, then go into deep learning, right? Make that gradual progression. Don't get overwhelmed or swayed by the hype that okay, deep learning is the in thing, because I see a lot of people only knowing deep learning but they don't know fundamentals. That becomes tough when you're working with real world data sets, because getting even, let's say, 80% accuracy can be a challenge there. So that is where knowing the fundamentals helps. So stick to your roots, stick to the fundamentals, but don't hesitate to explore. Follow the T-shaped model, I think, which Andrew Ng says. I mean, all of you know him, right? He's one of the best out there. So follow that T-shaped model where you go into the depth also with regard to the concepts, how to apply the models, so on and so forth, but also you explore the breadth with regard to natural language processing, computer vision, machine learning, deep learning, maybe reinforcement learning. So in that way, what happens is you have a wide skill set, and basically, if you're looking for a career in data science, you would be desirable, let's say, to be an asset to most companies out there, right? So that is the best advice I can give you. And basically, don't get frustrated. Sometimes it can get frustrating, but that is how every field is. So just hang in there and continue learning. That is what I'll say.
Yeah, totally. I second that. And thanks a ton for those valuable words. And it's our pleasure to have you here. And also on the other end, thanks to Professor Julian and Raviraj and Gunika for addressing and moderating questions on YouTube live chat.
Thank you so much.
Yeah. And thanks a ton to everyone who attended the session for being such an amazing audience. Till next session, thank you and goodbye.